Hello guys, and today's video is inspired by integral calculus. Okay, specifically by the book that you're seeing on the screen at the moment. Notice that this book is not only written by H.B. Phillips, but also, guys, this book is from 1917. Let me repeat that again, 1917. It's a really old book. I have this weird fascination for all math books, and when I try problems from these books, it kind of feels like I'm traveling in time. Okay, so it's just a weird thought that I want to expose out there for no good reason. Okay, anyhow, this is a very interesting book. Let me show you what it looks like. That's the preface, table of contents. Here it is. It's not a huge book, hence it's integral calculus, just one piece of calculus. Usually the second part. So this book, let's see, what else can I say? It doesn't have a lot of color, not a lot of pictures. Actually, I don't think it has any pictures other than just the diagrams, which I think is pretty cool. I feel like, many modern books out there, they put too many pictures, too much color for me. And I like color. It's just that it almost feels like this is a rant. It almost feels like they want to fill up the page for no reason with a bunch of stuff, and then, somehow charge you more for that. So I really appreciate that this book it's not in that doesn't have that intention, I guess. What else can I say? It's well written, goes right to the point. There's no proofs though. I noticed there's no proofs here, or at least I haven't checked it all. Maybe there's some proofs at the end of the book or something, but at least this first couple of sections there's really no proofs. And let's see what else. Oh, the problems. I've tried a couple of problems from this book. Some of them are really easy, but some of them are really difficult. Okay, which I really enjoy that. All the solutions of these problems are in the back of the book. They don't play this game of just having, or just presenting the solutions of the even or the odd problems. Okay, they don't play that game, which again I think that's pretty cool. Versus modern books that only have solutions for the odd ones or the even ones. Okay. All right. So you're here for one purpose, and that purpose is to know the derivation of Newton's law of cooling, which, by the way, I got from the book. Okay. So I want to show you that now. And there you have it. That's the formula that you can find pretty much anywhere, any books, Google, and it's the formula, I believe, the one that is taught in school and also college level. But remember, the purpose here is to show you how we get to that formula. All right. So before I start, we must know something, which is that Newton noticed that the rate of change of temperature with respect to time is proportional to the difference between the temperature at the moment minus A, which in this case represents the temperature of the environment or the air. I've looked at the definition in many places, and some of them say the temperature of air, some of them say the temperature of the environment. Okay, so what to do now? Well, I'm going to get rid of the d of t that you see there in the bottom. I have your d of theta, negative k. When I say get rid of it, I'm just going to pass it to the other side, okay? Times the difference between theta minus a times d of t. Now I'm going to pass this little difference to the bottom of the d of theta. So now we have d of theta over, or on top of, theta minus a minus k times d of t. Notice that we are in a perfect scenario to integrate both sides of the equation. So I will do so. Once I do that, I get from this part of the equation ln theta minus a. And now this is equal to negative k times t plus some constant c. All right. I want to get rid of that ln. So I'm going to exponentiate. Hopefully I'm saying that correctly. I'm going to exponentiate both sides of the equation. So now we have e to the ln of theta minus a equal to e to the negative kt plus c. Okay. These are going to cancel, so now I have theta minus a equated to e to the negative kt plus c. But this, notice, can be written as e to the negative kt times e to the c. Now, look what I'm going to do now. I'm going to, in a way, I guess, force an initial condition in this equation. I'm going to claim that I'm going to look at an object at the moment of t0, if that's possible, t equals 0, and which then means that my temperature is going to be zeta of 0, or initial zeta. I'm going to stick with the name initial zeta, right? So if this is the scenario, and I put all the situation in the equation that you see here on top, then I have zeta, initial zeta minus a, which is equal now to e to the negative k times 0, remember, t0, times e to the c. Notice that's 1. So now I have zeta, initial zeta minus a, equated to e to the c. This I'm going to plug in into here. All right? So that means that now I have that zeta minus a is equal to this right here, initial zeta minus a, times e to the negative kt. All right? So the only thing I have to do now is pass that minus a to the other side. So zeta here equates a plus initial zeta minus a times e to the negative kt. And there you have it. Notice that this right here represents t of t. This a represents TS, or temperature of the room or the environment. This right here is initial temperature of the body or object being observed. And this T of S is the same as this T of S, in this case, my A's. And the e to the negative kt, it's right there. And there you have it. That's the derivation of Newton's law of cooling.